Hair away. This is problem 1664, ways to make a fair array. Let's get right into it. So you're given an integer array nums. You can choose exactly one index, 0 indexed, and remove the element. Okay, so I have this array, and I can remove the element. When I remove the element, all the elements to the right are going to get shifted over 1, right? If you have items 1, 2, 3, 4, 5, and I delete, this 1 as index 0, 2 as index 1, 2, 3, 4, right? 4 is in index position 3, 2 is in index position 1. If I was to delete 3, then the new array would end up being what? It would be 1, 2, 4, 5. And you'll notice that everything after 3 got shifted over 1, right? Because 4 is now in index 2. It used to be in index 3. 5 was in index 4, and now it's in index 3. So everything gets shifted over to the left 1. Okay, for example, this, right? If you remove index 1, you have this. If you remove index 2, you have this. Choosing to remove index 4 gives you this, right? So you remove index 1, then the item at index 1, which is 1, gets removed, and you have this. If you remove the item at index 2, 0, 1, 2, so you remove 7, now you have this. So far, hopefully that makes sense. An array is fair if the sum of the odd index values equals the sum of the even index values. Return the number of indices that you could choose such that after the removal, nums is fair. Okay, so when you look at this example, so let's look at nums equals 2, 1, 6, and 4. Now, if I was to delete, let's put the index on top, right? So these are the indexes of each of the items, right? If I was to delete 2, right? So if I delete 2, or not delete 2, let's use the correct language here. If I delete the item at index 0, so delete index equals 0, right? I'm going to get 1, 6, 4. But everything has been shifted over 1, right? So this is now 0, 1, 2. The sum of the even is the sum of item at index 0 and item at index 2, which is 5. The sum of the odd is 6, so 5 does not equal 6, so it's not fair. And similarly, if we delete index equals 1, now we have 2, 6, 4, and 0, 0, 1, 2. And for this example, the sum of the even is 2 plus 4, which is 6, and the sum of the odd is just 6, so 6 equals 6. We're good. Interesting. And then I'm not going to go through the rest. I think it pretty much makes sense, right? We've shown an example where it's not fair. We've shown an example where it is fair. But you can keep going through that process and check every single index. So the n-squared solution here, right, would be to the brute force solution, which is not going to meet time constraints, right? Because if you had an n-squared solution, that would be 10 to the 10, right? Because this is 10 to the 5, so 10 to the 5, 10 to the 5, 10 to the 10. That is far too many computations, and it's going to result in a time limit exceeded error. So the n-squared solution is, right, you would just take the array, remove the number, then count all the evens, count all the odds, check if they're equal. If they are, add 1 to your solution. Go to the next number, remove that from the array, count all the evens, count all the odds again, check that information, and if they're even, add 1 to your solution. And you would do that for each number in the nums, right? So for each number, you'd have to look at every other num, right? So for each num, you have to look at all the nums, minus 1, because you don't have to look at the num you just removed, right? So for each number, you have to look at number nums, right? So for each number, you have to look at the length of the array, so that's n squared, right? So with that, we know that it's not going to work. So what would be a better solution to get us in a boundary which would meet the time constraints of this problem? Well, the first, I guess, observation you should make, and it's kind of the only observation that I needed to solve this problem, is that when you remove an element, only the elements to the right get adjusted. And how do they get adjusted? Right? So if we had a sum like this, right? Let's just say we had generic numbers A, B, C, D, E, F, G, H, I, J, for example, right? So these are just numbers. I'm just using variable letters to represent the numbers, right? If we looked at all the even numbers, right? The sum of all the even numbers, you would have A plus B, or A plus E plus C plus E plus G plus I, right? So A plus C plus E plus G plus I, right? Because it's the sum of the even indexed elements. Right, so we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, because A is in index 0, C is in index 2, E is in index 4, G is in index 6, I is in index 8. So this is the sum of the even index elements. Right, and then if we did the similar thing for odd, right, we get B, I'll do it a little bit different just so it's a little neater. B plus C, D, J, right? This is the sum of the odd elements, right? So looking at the original array, this would be the generic sum for the even elements. This would be the generic sum for the odd elements. What's interesting, right, is when you remove a character, what happens to this odd and even pair within the system, right? So if I was to remove, let's say, E. So I wanted to, why did I do that? Let's do X out. So if I wanted to remove E, what would that mean for the new array that's created? Well, remember I said that when you remove an element, everything to the right gets shifted over one to the left, right? Because this new array, if I looked at it, right, this would be index 0 still, 1, 2, 3. We've removed E, so now this is 4, 5, 6, 7, 8, right? And what would be the new even odd sum array for this new system? Right, well, for even, for this new system that we're creating where we've deleted E, right, would be A plus C plus what? F plus H plus J. And what I'll do, just to make things look a little clearer here, and then what would odd be? Odd would be B plus D plus G plus I. And then I'll play the same game. And I'll move these over one so that things are matching on the columns with respect to the columns. Right, does that make sense? Because I've literally, all I've done, right, is I've deleted this element 4, and then I wrote out the indexes for this new array where I've deleted the index at initial element 4, causing everything to the right, right? F was in position 5, now it's in position 4. G used to be in position 6, but since something before it got deleted, it got moved over one to the left, so now it's in position 5. And then I just wrote out, what the new sum would be given that we've deleted E. So what is the relationship between this green sum and this red sum? And intuitively, why is it like that? Well, you'll notice that the even, right, is the same up to here. Now, since we removed E, obviously there's not going to be the E in this new sum, right? Because we removed it, so it shouldn't be in our new sum. But then from this point forward, it's actually the odd sum, right? And then when we look at odd, right, it's the same as the original odd, but then after a certain point, it becomes what used to be even. So it's like when you remove an element, things get split up, right? It used to be just all even, all odd. Now even is like partly the original even plus some components of odd. So why is it like that? Well, intuitively, right, when I remove an element, right, when I remove 4, everything to the right gets shifted over 1 to the left. So everything that used to be even to the right becomes odd. And everything to the right that used to be odd becomes even, right? Because if f was a 5 before, if it was an index 5, now it's going to be an index 4. So now it's even, right? So everything to the right like switches positions, right? When I look at my initial sum, everything to the right of the element I'm deleting, if all of that sum that used to be even will now be odd. And likewise for odd, right? Everything that used to be odd will now be even because it's to the right of the element. Versus everything to the left stays the same, right? Because E was in this position. So since I removed E, everything to the left didn't shift over at all, right? A is still in position 0, B is still in position 1, C is still in position 2, D is still in position 3. So those things stay the same. So everything to the left of what I've deleted stays the same. What used to be even is still even. And everything to the right of the position that I deleted used to be odd becomes even. If it used to be even, it becomes odd, right? Which is why you have this weird switch, right? So AC, you delete the element. FHI, delete this element. Okay. So what is the relationship of this with respect to the initial summation? Well, if you delete an element, so I guess what you could say is, I'm trying to think about how I'm going to articulate this. Even when you delete, even without E, right? Because we deleted E here, is going to be the sum it's going to be the sum of even before E, right? Plus the sum of odd after E. Does that make sense? Because the even without E is the sum of even before E, right? So since we deleted E, the sum of even before E is A plus C, right? Because E is here. So the sum of even before E is A plus C, plus the sum of odd after E. So since we deleted E here, right, the sum of odd after E is here. And likewise, the odd value without E equals the sum of odd before E plus the sum of even after E. Right, so when I delete E, right, the odd is the same, right? The sum of odd before E's place is B plus D, plus the sum of even after E, which is G plus I. So I'm basically saying if you remove a character, this is the relationship to the original summation, right? Which makes sense, right? Because if I'm looking at what's even, the sum of the even indexes without E, well, it's going to be the same as everything before because none of those get shifted. But now everything to the right of E is going to get shifted over 1 to the left. So now those odds become even. So what used to be odd becomes even from the right side. And what used to be even stays even if it's the left of the element. And same with odd, right? So everything to the left stays the same. Everything to the right switches, essentially. So then how would we deal with this in code? Well, I'm going to introduce 2 ideas. I'm going to introduce one idea that the time complexity is optimal. The space complexity is suboptimal, but it's probably easier to understand. And then from there, I'll suggest, or I'll even write, a second solution where the time complexity is still optimal and the space complexity is also optimal, just by tweaking the solution a little bit. So in order to kind of keep count of what's going on here, right? if we had A, B, so let's look at this example again. So if we had A, B, C, D, E, F, G, H, I, we could keep like a prefix sum, and in each element we keep the sum of even up to that point and odd up to that point, right? Because we need the sum of even before E, right? And we need the sum of odd after E. So if we use like a prefix sum, meaning like we keep account of what's the sum of even up to a point, what's the sum of odd up to a point, we can keep track of essentially what? We can keep track of these values here in constant time, right? Because this would still be an n-squared algorithm if you didn't pre-compute the sum of even before P and the sum of odd after E, right? Because you would remove E and then you'd have to count the sum of the evens before E and then count the sum of odds after E. But if you use a prefix sum, you can pre-compute these values. So let's pre-compute these values so that this is a constant operation. That's essentially what I'm saying. So if you had even here, right? What would the sum of even be here? It would be A, right? In this position, it would still be A, right? Because since it's even, we don't count B. What's the sum of even up to this point? A plus C. What's the sum of even up to, let's make this look really cool. A plus C. What's the sum of even up to this point? Well, we don't add in the D, right? Because the D is not even. So it's A plus C up to this point. A plus C plus E up to this point. A plus C plus E up to this point. A plus C plus E plus G up to this point. A plus C plus E plus G up to this point. A plus C plus E plus G plus I, and then up to this point, A plus C plus E plus G plus I. So it looks pretty cool, right? So I'm saying at this point, right, I know at this point the sum of evens is A plus C plus E. Up to this point, it's A plus C plus E, A plus C plus E plus G. You know, up to this point, it's the same thing. And then for odd, we play the same game. So maybe we can make this a little cleaner. And then I'm just doing this with general letters, just so you can fully see how this is supposed to work, okay? It's always good to use variables because it lets you kind of make a general argument about how things work. All right, so we'll play the same game for odd. See if I can grab this. All right, so let's play the same game for odd. I messed up because I just kind of messed up the... Okay, whatever. That's good enough. All right. So odd up to this point is nothing, right? Because there is nothing to add. I won't put 0. I'll just put nothing there, right? Because there is no odd letter because this is the first letter that's in an even position. So to here it's B. Then it's B. Then it's B plus D. Then it's B plus D. Then it's B plus D plus F. Then it's B plus D. So I'm just doing the same thing we did before. B plus D plus F plus H. Then it's B plus D plus F plus H. And then finally B plus D plus F plus H plus J. So just like this, I have this prefix sum idea, right? Where I can easily calculate what comes before something and what comes after something. So E is in position, let's just put me over here because who cares? So if I did this calculation again, E even without E equals sum of even before E plus sum of odd after E, and then odd without E equals sum of odd before E plus sum of even after E. If we look at this example, right? Well, what's the sum of even before E? Well, that would just be the previous element, right? So if E's in position, so if we didn't say index, right? So E's at what index? So index of E equals 0, 1, 2, 3, 4. This equals 4. So let's do this problem with respect to indexes, right? So even without E would be even before index 4. So that'd be the sum of even before index 4. Sum of index before index 4, after index 4. Okay. So if we try to figure that out before 4, so that would be, okay, we're looking at E. So that would be 0, 1. So that'd be even at index of E minus 1. Right? This would be the sum of even before 4. Right? Because that's the first thing we needed. And then plus, so I'm solving this problem here, if that's not completely clear. Why'd I do before? Just index 4. I don't know what's going on with me today. Okay. So that's the sum of even before 4. Okay, then in order to find out what the new even is, so let's do that. So even without E equals the even of index E minus 1. So the sum of even before 4, that's what this information would give you. Right, because the sum of even before 4 is this position, which is A plus C, plus we said it was odd after E. Well, the sum of odd after E is a little bit trickier, right? Because the sum of odd after E is not B plus D plus F, right? The sum of odd after E is supposed to be G plus I. Or wait. The sum of odd after E is F plus H plus J, right? So that should be what our answer is. So if instead we did this, right? Because what we really want is F plus H plus J. So what you'll notice is, well, that's the same thing as if we took the end of the odd system. Let's make this a little bit wider. So we took the end of this system here, right? And then if we delete it, we want F plus H plus J. So then we deleted what was already odd up to even E, right? So if we removed this, then it would remove this, and then voila, you get F plus H plus J, right? So you're just doing a difference. So if you just then, in order to get the odd, if you want the odd after something, odd after E, that's the same thing as taking the total odd minus the odd at E, right? Because it's a total sum, so you're just taking the difference, right? So you take the odd of the whole system, so I'll just call that odd of -1 using like a Python notation. And then you'll subtract out the odd at the index of E. So that'll give you the even without some letter E, right? And then we can play a similar game for odd without E. So if we've already pre-computed this stuff, all of these are constant operations, right? So this is a constant operation, this is a constant operation, this is a constant operation, and we just have to do this for each number, right? So that would mean that we only have to do this process n times, but for each of those n times, it's a constant operation. So that basically takes our algorithm from n squared to n. Okay, odd without E. So let's play this game again. Well, to find the odd without E, we want to find the sum of odd before E. Right, so if you want the sum of odd before E, that would just be odd at the index of E minus 1. Right, because that's just this information here, B plus D, right? Because I'm trying to think about, it doesn't matter. Okay. Plus what? Okay, and then, so that's the elements that are odd before E plus the sum of even after E. So to find the sum of even after E, we played the same game. So the sum of even after E so we take the full sum of this system, because what we want out is what? G and I. Wait. Yeah. We want G and I out of this system. So then we delete G and I. So we want G and I at the end. So then if we delete out what's at E, we delete this out, and then what's remaining is G and I. So if we take even, the last value of even minus even at the index of E. So then these are the two formulas to find that information, and then to see if they're equal, you would just say, does this sum equal this sum? So basically this problem has two parts. We have to first, so the first thing we have to do is create this prefix sum for even and odd, right? And then we have to not make the square until after we write what we want to write, because we don't know what the size is going to be. I'm kind of an idiot. We have to look at each element, delete it, and check if the above are equivalent, are equal. Right, so this is number 2, right? Because we want to check, does this sum equal this sum? Because that would mean that without an element, the odd equals the even. Okay. Three, 4. I'm just checking my work to make sure that I'm doing this correctly. So please bear with me for a moment. I'm thinking about is what if the element is odd, like an odd index? Does that change anything? So what if, does this formula still hold if we're looking at like F? So let's look at F for example. So F, the sum without F, the index of F minus 1 is this. It's even without F, plus odd minus 1. Minus odd at E, B plus D plus F. Okay, that checks out. What about odd? Odd without F be this, or no. This odd plus even minus this, which would be G and I. Is that right? Yeah. All right. Sorry, I'm just proving it to myself. I should have articulated what I was doing more, but I'm just trying to make sure there's no difference when I'm looking at an even index and an odd index by using this formioli. So let's go ahead and calculate that prefix sum first. So we'll take nums. We'll have an odd prefix sum. And then we'll have an even prefix sum. And then we'll look at each num. We'll look at I, so we know that what index we're looking at, right? Because the index of the array tells us something be even or odd. We'll look at each num and we'll enumerate, so we can just easily look at each number. We'll say, okay, well the odd at this index equals definitely the previous odd. If what? Plus the current number we're looking at. So we'll add in the current number to the odd sum, because you'll notice here, right, like odd only increases if we're looking at an odd index, right? Like odd doesn't increase here because this is an even index, right? So 0, 1, 2. So since this is an even index, we don't increase odd. But then when we look at an odd index, we add in an additional thing. If we're looking at an even index, we just keep it the same. We look at an odd index, we add an additional thing, right? So we'll keep it the same. And then if we're looking at an odd index, we will add in an additional thing, and that additional thing is the number. So if the mod 2 equals 1. And then we do the same thing for even. This should be multiplied. This is basically saying, because if this is not true, it'll be 0, right? So if this statement is false, because we're not looking at an odd index, this will be 0. It'll multiply this by 0, so then we won't add in that additional thing. This is just a kind of annoying way that I do things to make my code short, and it's become a bad habit, and some people get very confused by it, but just bear with me. This is just kind of how I approach problems. So if the number is even, right, if the index we're looking at is even, then this will be true, which will cause this to be a 1, which will cause this num to be added to the current even sum. So we're only going to add in things when we're only going to add a number to even when we're looking at even index. We're only going to add a number to odd when we're looking at odd index. And then just so that you can kind of see that this works as intended, and you get a better understanding of, what's going on, and that this isn't just, witchcraft. We'll take a look at, okay, I did index for some reason. It's obviously supposed to be I. Okay, this is just an error because we're not returning anything yet. We're not going to worry about that. So the sum of evens, right, starts at 2. And then we look at an odd index, so we don't add an additional one. And then we look at an even index, so we add the 6. Then we look at an odd index, so we don't add the additional value. The first sum of odd is 0, right, because the first index is even. We get an odd index number, so we add in that 1. We get an even index number, so we just keep it the same as 1. We get an odd index number, which is 4, so we add in that 4 to the one that we had before, and we get 5. So this system seems to work fine. So it seems like we have successfully done this portion, right? Let's make it green because we're articulating that. Aren't tablets just so cool? Okay, so we've finished this portion. We've created this even and odd sum. Now let's run this formulae to see if we can find the number of cases where this is true, right? Because this, for any element, right? For any element, this will give you the sum of the evens without that element. So let's do that in terms of indexes. So we'll return the sum of something to do with an index for index in range length of nums. So we'll look at each index in the range of the length of the numbers. And then we'll do this calculation. So we say if the even of I minus 1 okay, the thing I'm worried about is what if you look at the item at index 0? So if I minus 1 is 0, so we'll just multiply this by int so I'm just doing this because I minus 1 could give you a negative number when I is 0, and then you could have a solution where it's going to consider the last element. It's just going to bug out. So we're just doing this to ensure that even of I minus 1 is as intended, right? It's the previous number. Okay, and then plus odd, sorry, I'm looking at my tablet here, plus odd of negative 1, so that's the sum of odd, minus the sum of odd at the current element. If that equals odd again times int I minus 1 greater than or equal to 0. Sorry, and I'm just copying this formula verbatim. I'll show you it in a second so that you can see that what I'm doing isn't just some crazy fool's gold. Right, so I'm just saying if this sum here, right, so this formula here, I minus 1 plus odd of I -1 minus odd of the index of the element, which is I, equals odd of index I minus 1 times this to make sure it's greater than 0, plus even at -1 plus even at I, and then you do that for each number. All right, so let's run that. Oh! Fudge. So what did I do wrong? Oh, this is plus even of -1 minus even. All right, I didn't have the formula right here, right? Minus here. Hopefully that's it, because I would look very foolish otherwise. Okay, so let's... Hey! Be mature. So this is good, right? So this solution is fine, right? The time complexity is O of n, right? Because we have to look at each number in nums to generate this prefix sum. And then we have to return that sum. And that's going to be another O of n. So it's O of n plus O of n, which is O of n. But then the suboptimal part of the solution, right, is that we have to create odd and even. And that's going to take O of n space, right? O of n space for odd, O of n space for even, O of n space total. And there's actually a slightly better way that we can think about this solution to kind of create constant space. Well, you'll notice that, I guess, I'm trying to think about if I want to do this. All right, we'll do it here. We'll do it here. Sorry, it's always hard to know, like, do you want to do something in detail, or you just want to mention it because, you know, do you already understand it? Is it easy to understand? Am I wasting time? Kind of questions you ask yourself when you're articulating a point. So when we're looking at this, I don't know why I just did that because I'm an idiot. So we're looking at this part here. For an even without E, we just need the sum of even. And that's one thing to note when you look at an element, right? We want the sum of even before E, the sum of odd. This is just the sum of all of odd, right? And this is the sum of odd up to E. This is the sum of odd before E. This is the sum of even, the total thing. And this is the sum of even up to E. So to find out what something is at a character, we only need information about things that come before it, right? And then just one variable about the total sum of odd. What that basically means is we can sum through the array, look at an element, and we don't need to actually hold information about everything that occurs, right? You only need information about everything up to you and the total sum. So you can look at each thing and just keep one or two variables that keep information about everything up to you, and you don't need to save additional information, right? To calculate information related to I, you don't need all this previous information here, right? You just need information about information up to I. Does that make sense? So I don't need, like when I calculate, for example, H, right? I want the sum of the elements, or let's say I, right? Or 8. So hard for me to think about what I'm going to do. Okay, so if I'm looking at H, what's the sum without H, right? Well, I want to take the sum of even before H, which is this, right? And then I want to take the sum of odd, which is this total thing, and I want to subtract out the sum of odd up to H, which is this, right? And then when I want to find odd, so that'll give me even. If I wanted to find odd, I need this odd of it up to this minus 1, plus the even of the whole thing, which is this, minus the even at index E. And we're looking at H, which is this. Right? So there's only like 6 things I need, sort of, right? All this other information is not relevant anymore, right? None of this matters anymore. I don't need any of this. Right? I don't need this. I don't need any of this. I don't even really need this information, right? Because I can calculate that later, right? When I get there, then I can calculate that. I just need the sums of the whole systems and the sums of even up to this point and the sum of odd up to this point. So that means that, well, I can say, okay, the sum of even minus me would be instead just some even sum that I've counted so far minus the current number. Okay, well, yeah, it would just be the sum of even so far. Sorry, and now I'm trying to think about something. So I'm trying to think about the best way of doing this without making it too complicated. Yeah, okay, that's fine. So that would be the sum of even without me. So this could be changed to an even sum minus the current element, if the current element is even. Because if it wasn't, then it won't be added to the even sum. It really depends on how you want to do it. Ugh. We'll do it like this. So the sum of some even thing plus an odd sum, which is the sum of the whole system. So that's what this will get replaced by. So we can just calculate the odd sum once and then use it for the whole problem. Minus the odd sum up to this point. But you would want to add in the number if the index is even. All right, so if index is odd, actually. Because that means the odd sum is now higher, right? Because the odd sum will only increase if you're looking at an index that's odd. That's the best way I can kind of describe this here. All right, so that would be your new even solution. And then for odd, well, this would just be the current value of odd. Plus this will just be even sum. And then your new even would be your even sum plus the num if the num is even, right? Because the point I'm trying to get at here, and I don't know the best way to articulate it, is like, if you're looking at a current index and you want to know what the even sum is, the even sum will be the same if you're on an odd index as the previous thing. But if you're on an even index, the even sum is going to increase by 1. So that means that, you know, odd, right? Because, okay, odd of index of E, the odd of an index is the same as the odd of a previous index if you're on an even index, right? Right? The odd of an index is the same as the previous index if you're on an even index, right? Because this G is an even index, so the odd sum is the same as the previous one, right? So in that case, if index is odd, then this sum will be the same as this sum because this will get zeroed out. That's the best way I can describe it. It makes sense in my convoluted of a mess brain, but maybe watch that in a half speed and walk through. It's a lot of like conditionals, like if odd, then even it. But hopefully that makes sense. So with that, let's just use this notion to find the solutions. So that means our problem's going to change a little bit. First, we should calculate our odd sum. So we'll say odd equals even equals this. And then we'll set odd to be equal to 0 instead of keeping count. So this will be our odd sum, sorry, even sum. So we're going to use this first loop to just figure out what that information really is, right? We'll keep it on 2 lines for now. Let's not get crazy. So we'll say odd sum plus equal even sum plus equal. All right, so this will give us our odd sum and even sum of the entire array. And then we can just play this game where let's create a current even value and a current odd value. And then we'll have res equals 0. That'll be our solution. Okay. And then we have to do this again. So we look at for I and num in enumerate nums. We'll play this game. So res is a solution if this equals this, right? So even so far, plus odd sum. Let's okay, let's do this just so it's easier for me to just see both, because it's kind of annoying to go back and forth. Okay. So res plus equal 1 if even plus odd sum minus odd plus num times int I is if index is odd. So if I mod 2 equals 1. And that'll be good if what? Let's put this in here. Sometimes I do the most ridiculous things, then it's like super confusing. I don't know why I do this to myself and to others. Okay, if odd plus, this is getting, if odd plus even sum minus even plus num times if the number is even equals 0. And then after we're done with that, we will just update even plus equal num if the number is even, and odd plus equal the number if the number is odd. And then at the end, we'll just return res, because res will be at a counter that accounts for each of the solutions. Oh! And there you go. So what's the runtime and space complexity of this problem? Well, it's still O of n, right? So I have to do O of n time complexity operations for this, O of n time complexity to operate to determine this. So for time, let's just say that n equals length of nums, and let's say that time, well, that would just be O of n, which makes sense, right? Because you would have to look at every number regardless, right? There's no log n of solution. You have no other information about what nums looks like. You just know that nums exist. So you're not to look at every number, right? So it makes sense that it's O of n. Because how else are you going to process the sums if you haven't looked at the actual numbers? And then for space, we have O of 1, right? Because we only have to use these 5 variables, right? We don't actually have to create any additional variables to solve this problem. So by using this kind of tricky solution, we have gone from O of n space complexity to O of 1 space complexity. Okay, and so that's pretty much it. That's this problem. What I'm going to do now, you can end the video here, totally understood, but I'm going to make this solution super short just to be annoying. Just to show you that it can be done, that everything's possible. I could even make this actually, do some nums at I, or I in range. 0. Oh, that's awesome. 1 length of nums, counting by 2. Alright, and then I could change this one too. Starting at 0. So that means I can get rid of this. And that's technically one line. Don't let anyone tell you different. And then even res equals res plus this. And I could say even equals even plus this. And then I could say odd equals odd plus this. And then technically speaking, I could put all that on one line. So this is technically 3 lines. Okay? It's a 3-line solution. It's a beautiful thing you can do with Python. Look at that. 3 lines. Constant space, linear time. If you did this in an interview, they'd probably yell at you. But if you did it at the end just to say, like, look what I can do, they might find it comical. But if you have extra time, maybe. All right, guys, have a good day. I feel like this was an all right video. There was definitely some points where I struggled to describe my processing, but what are you going to do?